Hi, everyone. This is a lecture. It's Chapter 6, Part 1. Chapter 6 is on fluid dynamics. I'm going to start the lecture today with a video. Let me share my screen. Let's see which window. Geez, which window would it be? It's like the window's not showing. Oh, maybe because it's not open. Okay, so let me go back to this. Sorry about the delay. Yeah, there it is. I didn't have the window open, so it didn't like that. Now it's there. It is. Okay. All right. Okay, so here's this video. It's from Ryerson University. And this, I think that's in Toronto. I think it was from a class, a fluids class. And the guy talks, it's really good talking about the different applications of fluid mechanics, but the guy talks really slow. So, okay, so I've set the playback speed to 125, 1.25. So this should take about 5 minutes. I think you'll find it really interesting because before I cover fluids, I want to talk about like why fluids is important to mechanical engineers. So let's go ahead and, I just realized that when I shared my screen, I did not share my audio. So let me do that again. This time include sound. And there is Chrome. Okay, so now hopefully this should work. Okay, I'm going to play it.
Okay, welcome to MEC 516, BME 516, Fluid Mechanics 1. Before I get into the deeper technical content of the course, I thought I'd start by talking about some of the common engineering applications for fluid mechanics. Hopefully this will give you some idea of why it is important to learn fluid mechanics. Maybe it'll inspire you and pique your interest in this topic, which I think is fundamentally pretty interesting. A very common application, especially for mechanical engineers, is heating, ventilating, and air conditioning, HVAC. Fluid mechanics considerations are central to the design of furnaces, air conditioners, heat pumps, and even fans and ducting systems. In fact, there's a fourth-year course for mechanical engineers in HVAC. I believe it's an optional course. All buildings require some sort of HVAC system, and large buildings would have very complicated heating, ventilating, and air conditioning systems. So there's a lot of employment, especially for mechanical engineers in this area. Industrial pump and piping systems also involve fluid mechanics principles. So, for example, here you might be selecting a pump in order to get the desired amount of flow rate, or you might be sizing the piping so you don't have too much pressure drop along the pipe. We'll get into some of these issues in detail in this course. There are also a wide range of fluid mechanics problems in the transportation sector. Of course, with aircraft, you're concerned with the aerodynamics of the flow over the wing that keeps the aircraft in the air. There's also flow through the turbine engines that provides the thrust to keep the aircraft aloft. Aerodynamic drag, for example, is important in designing cars, especially sports cars, and on boats. Wave drag would also be an important consideration in terms of how much power it takes to drive the boat through the water. These are all key fluid mechanics considerations. Fluid mechanics is also central to the design of electric power systems. Here we're talking about coal power plants, natural gas power plants, and nuclear reactors. There is fluid flow in boilers, in condensers, and in the nuclear reactors themselves. A common everyday application is the electronic cooling of the computer that you're watching this presentation on at the moment. This is usually done with a fan blowing air over a heatsink of some sort. And nowadays, this can be analyzed using a technique called computational fluid dynamics, which I'll talk about a bit in this course. because of concerns over climate change and other environmental issues, there's a growing interest in renewable energy. It's certainly a growing field. And fluid mechanics is central to the design of many of these renewable energy systems, systems like solar thermal collectors, in other words, hot water solar collectors. It's central to the design of course, the blades of turbines, which is all about the aerodynamics. Fluid mechanics is also important for things like the design of hydroelectric power plants. And it's also important for things like geothermal systems. Fluid mechanics also arises in many biomedical applications. So the study of fluid mechanics is necessary in order to understand flow in the cardiovascular system. Here, of course, the two main fluids that we're talking about are blood and air. And it turns out that blood is a rather unusual fluid, and I will talk about this later in the course. Also, the heart is a biological pump. One of the more exciting aspects of learning fluid mechanics, I think, is that it's a gateway to learning computational fluid dynamics, which is a more advanced topic. Computational fluid dynamics is the numerical solution of the equations of fluid flow, the so-called Navier-Stokes equations, which we will talk about in this course. And nowadays, most mechanical designs involving fluid mechanics are done using CFD. Let me start this little video here. This is a solution of fluid flow over a small vehicle. And of course, the idea here would be to predict the flow patterns and the aerodynamic drag with, of course, an eye to minimizing the aerodynamic drag on the vehicle. And there are some really nice commercial solvers out there, commercial software for engineering design involving CFD. One's called COMSOL, another one is ANSYS Fluent. But CFD goes quite a bit beyond mechanical design. Nowadays, your daily weather prediction is really made using computational fluid dynamics. Here we're solving the complex flows in the atmosphere. It's also been used extensively for climate modeling by NASA. And here in this image, it's showing what's called the global circulation of the atmosphere. And it's a prediction by NASA as part of their efforts to predict the effects of climate change. CFD also comes up in movies and advertising. It's called computer generated imagery. And you've undoubtedly seen this in movies by Pixar and Industrial Light and Magic. So nowadays, instead of building physical models, you actually build a numerical model and solve the equations of fluid flow. And this is just a little example here. And you can see that, this is completely virtual, but it's surprisingly convincing. To conclude this general introduction, I thought I'd talk a bit.
Okay, so that is what I wanted to show from this video. Sorry, just had to take a Tylenol. Okay, so I'm going to stop sharing screen and let me start sharing a different screen. I'm going to share my iPad. So share, except this time the window will be my iPad. Okay, super. All right, so we are talking about Chapter 6, Fluids Engineering. As I think that video described, there's a lot of aerodynamics, biomedical, piping systems. He didn't get into microfluidics, which is really popular in biomedical engineering. He talked a little bit about biomedical, but the microfluidics, that's where they do genomic research and also pharmaceuticals. So there's lots you can do with fluids knowledge. And then sports, the design of golf balls, analyzing ski jumpers, racing cycles, marathon runners. There's a lot involved in fluid dynamics in that as well. So let's talk about fluids engineering. So what is a fluid? So different scientists and engineers will define it differently. So I'm going to talk about this obviously from an engineering standpoint. A fluid is any substance that is unable to resist a shear force without continuously moving. So it's unable to resist a shear force. Let me go ahead and underline that. Unable to resist a shear force, because that's key. The study of fluids, fluids are either classified as liquids or gases. And we'll talk a little bit more about that when we talk about the compressibility. So there's two different types of fluids. If you just say fluids, you're encompassing both liquids and gases. And you can break it into fluid statics and fluid dynamics. Fluid statics refers to the behavior of liquids and gases when they're moving or when the object is moving through them. And fluid statics, that's more talking about pressure and buoyancy forces acting on stationary objects. And you're going to be learning both in the program. And then here is a picture of, of Jupiter. And here, see the giant red spot? How do you think they predict the motion of the giant red spot? It's according to fluids principles. And so fluids dynamics can be on a very, very large scale, planetary scale. And then it could also be microfluidics, which I mentioned in the last slide. Now, it's kind of interesting. 98% of electricity is produced through fluids engineering. So 98% of electricity. This includes 88% from the cycle from liquid to steam. And back again. This cycle of taking water from liquid to steam to liquid to steam to liquid to steam, that's where we get 88% of our electricity. And so it involves the motion and the change of type of this water. And then 7% is through hydroelectrics. So when you first think about fluids and how fluids would be involved in energy, you might think dams. And yeah, that's absolutely true, but that's actually only 7%. 88% is through the fluids engineering, the water cycling. And then the rest of this 98% would come from wind power, which is also fluids engineering. So now let's talk about the properties of fluids. So fluids are categorized as either being liquid or gas. And what's the difference? How would you, I kind of like we know it when we see it, but how would you characterize a liquid versus a gas? Well, there's one big difference, whether or not they can be compressed. A liquid cannot be compressed. You can push on it and push on it, but it's not going to be easily compressed. Liquid, this would be incompressible fluids. But gases, on the other hand, are compressible. And so when you study fluids, you'll be distinguishing between incompressible and compressible. I've had quite a bit of exposure to this in recent years through the hydraulic bike competition team, because they need to do hydraulics because the bike is hydraulic powered, so they've got the hydraulic fluid that they need to analyze and design with. But then they also have a pneumatic component. And these two things combined are what we often call fluid power. So fluid power would be the combination of pneumatics and hydraulics. Okay, and fluid power, that's just one aspect of fluids that you'll be talking about. Okay, now let's talk about flow. The primary difference between a solid and a fluid is the manner with which it behaves when subjected to shear force. So it's all about the shear force. I think I underlined that a couple slides ago, the shear force. A fluid responds to shear flow with continuous motion that is called flow. So the continuous motion in the presence of a shear force, that is what flow is. Now let's talk about a no-slip condition. A no-slip condition occurs at the microscopic level between a solid surface and a fluid that's in contact with it. Okay, so the no slip, what this is implying is that the layer of fluid that's in contact with the surface remains stationary while the uppermost elements will move. Okay, so let's get out our, sorry, I guess I had not brought this up. So this is about the no slip condition, but I actually want to draw a diagram on this. So get out your pens and your paper if you don't have it already. Okay, so let's draw a surface. And let's draw like a moving plate on top of it. Okay, so this is a moving plate. And let's say that the plate has a force on it, like that. And let's say that between the moving plate and the surface, you have a bunch of oil. So the oil is a liquid. I am just going to show it with a bunch of dots here. Okay, so this is oil. The no-slip condition means that if you were to pull the plate to the right with this force, that the oil that's along the plate will move, but the oil that's not along the plate will not. And so here's like the velocity profile of the oil. It looked like this. I feel like this is kind of hard to see the green on top of this. So this is the velocity of the oil velocity. So at the surface, you can see how here it's 0. And then the maximum would be along the plate. So this is what's called no slip condition. And a really good analogy to this, a fluid analogy, would be to think of playing cards. You should be writing this down. If you sheared playing cards, okay, so let's say that I have my surface here, and on my surface, I have a deck of playing cards. So you can imagine there's a whole bunch of playing cards. And this would be my before condition. If I were to put a force on this, you can imagine what would happen to the cards, right? So if this is my after down below, and here's my surface, the cards will go something like this, right? In a no slip condition. So this is what we're talking about, a no slip condition with the force being applied. So the no slip condition is shown here, and also it's shown over here with the oil. Okay. So let's move on. The next topic will be viscosity. Viscosity is a physical property of all fluids that enables them to resist a shear force by developing steady motion. Okay, so experiments show in many cases the magnitude of a fluid's shear stress is directly proportional to the plate sliding velocity. Such substances are called Newtonian fluids, and they satisfy this relationship. So over here, tau is equal to shear stress. Please note that. So you guys should write this down. Tau is equal to shear stress. The relationship is that tau is equal to mu times V divided by H. So mu is the fluid's viscosity. So write that down. V is the velocity. And H is the height of the fluid. So the viscosity relates the fluid's shear stress to the plate speed. Because the viscosity property arises frequently in fluids, a special unit has been developed called the poise. And the poise is 0.1 kilogram per meter second. And so you could also use just kilogram over meter second or slug over foot second. But if you wanted to, you could also call that the poise. When you get into fluids a lot, you'll be using the poise. Okay, now let's talk about pressure and buoyancy. We're just going to talk about just a couple more topics, and then we're going to do some problems, and we'll see all of this being applied to real life. Okay, so the force that develops when an object is simply immersed in a fluid is called buoyancy. The buoyancy force, and it's related to the weight of the fluid that's been displaced. So the buoyancy force equals the weight of the fluid that's been displaced of an object. So let me go ahead and put a box around this. So the buoyancy force, we'll call that F sub B for buoyancy, is equal to the weight of an object. Well, what's the weight going to be? Well, it's going to be the density times gravity times the volume of the object, where mu is the fluid's density, V is the object's volume, and G is gravity. A couple of little bookkeeping notes on this. Be very careful to use, I'll just write it down here, careful. Mu is equal to density. P is equal to pressure. You've got to distinguish between those two. Also, little v is velocity. Big V is volume. So you really have to write clearly to be able to even follow your own work, let alone have somebody else follow it. All right, let's continue on pressure and buoyancy. So the buoyancy force is the weight of the fluid that's been displaced. And the pressure is going to be directly proportional to the depth and the density of the fluid. The pressure would have dimensions of force per unit area. So we'd use Pascal or PSI. Okay. So here we're looking at pressure and buoyancy force, and the pressure down and the pressure up, and how they relate. So let's go ahead and do I think it's kind of better, we'll be getting to these in a problem, so let's do that. Okay, so our first problem. The fuel tank in a sports utility wagon holds 14 gallons of gasoline. How much heavier is the automobile when the tank is full compared to when it's empty? So this is a good problem. So we are given SUV fuel tank. And it's 14 gallons of gasoline. And what we need to do is find the weight of the fuel. All right, we can do that. Okay, when you look at the textbook, you'll see that the weight, an equation for the weight is equal to density times gravity times volume. This is equation 6.3. So we need to know clearly what the density is of gasoline, right? So the density, if we look up in our textbook, it's 1.32 slug, because this is a customary unit problem, slug per cubic feet. This is in table 6.1. Look at this. We're going to be dealing in terms of gallons, but our density is in terms of cubic feet. So we're definitely going to need that conversion. So back in table 3.5, we use that in chapter 3. They had the conversion that 1 gallon is, let's see, 0.1337 cubic feet. That's from table 3.5. All right, so now it's just going to be pretty much as easy as plug and chug. So the weight is equal to density times gravity times volume. Density is 1.32 slug per cubic foot. The gravity would be not 9.81, 32.2. 32.2 foot per second squared. And volume is 14 gallons. And of course, we have to convert that, where we would say 1 gallon is 0.1337 cubic feet. So let's cross off our units. And I'm going to stick this in my calculator. So I have 1.32 times 32.2 times 14 times 0.1337. All right. Hold on, I did something wrong. 1.32 times 32.2 times 14 times 0.1337. That looks better. 79.56. So the weight is equal to 79.56. What are my units? Okay, so I'm hoping I get weight in pounds, right? But not necessarily. Let's see what we've got. So first off, I see that foot cubed on the end will cross out with the foot cubed that was in the beginning. That is all I can cross out. So the units here are slug foot per second squared. All right, is that going to be pound? Well, to convince myself, I always go back to this, that weight is equal to mass times gravity. Putting it in terms of unit, pound is equal to mass, which is slug, times gravity, which is foot per second squared. So yeah, a slug foot per second squared definitely is a pound. That is correct. So I'll give my weight is equal to 79.56 pounds. Cool beans. Growing up in Michigan, when the winter weather came, my parents would always have me make sure I try to keep my fuel tank pretty full. Have you heard this, that if you have a full fuel tank, you'll have better traction in the ice? I kind of think that was just an old wives' tale, but let's see. A totally full tank is like essentially 80 pounds. If my vehicle, I guess I had a Ford Escape. Now I have a Mach-E, so it's electric, so I don't have this calculation. But with my previous vehicle, I had a Ford Escape. And that is around 3,500 pounds. So this is 2.3% the weight of the SUV. So this is just 2.3%. So the impact on performance will be negligible. Okay. So it kind of is an old wives' tale that you need to keep your fuel tank full to have better traction. I mean, any little bit of traction helps. I'm just saying it's not going to make a big impact on the performance of your vehicle. So don't like depend on that for the performance of your vehicle. Okay, let's do another problem. Of course, if you have any questions on these problems, you can contact me. Okay, it says the pressure at the bottom of an 18-foot deep storage tank for gasoline is how much greater than at the top of the tank? Express your answer in units of PSI. All right, we can do this. Given we have an 18-foot deep storage tank. And it's gasoline. We need to do is find how much greater pressure is at the bottom of the tank. And we'll call that P, then top. And we'll call that P naught, P sub 0. Let's draw a picture. Okay, so a tank, we'll assume it's a round tank. So here's my tank. Draw it like that. And we have, let's say the fuel is this full. This is the pressure at the top, P naught, and this is the pressure at the bottom. Oh, and I also know that this is 18 feet deep. I'll call that H. All right. So in the textbook, we see when we get to the section on pressure, we see that P starting to think that this is inverted and P naught should be at the bottom. Yeah, I think it is wrong. Yeah, my diagram's wrong. Okay, so I'm going to change this. The bottom of the tank is P naught. I thought it seemed strange. The top of the tank is P. And over here, I'll change that too. Sorry about this. So P naught is at the bottom. P is at the top, or any part that you care about, and P naught is at the bottom. Okay, so the pressure at any point is going to equal the pressure at the bottom, so that's your P naught, plus rho GH. Is where you have to be really careful to make your rho not look like your pressure, like a P. Okay, this is equation 6.4. Oh, wait, I am wrong. Hold on. Oh, I'm sorry. I am wrong here. I was right originally. I should have trusted what I had initially. I hate it when you do this. Okay, I'm so sorry. So, but let's think this through. What's going to have the minimal pressure? The top of the tank or the bottom of the tank? The top of the tank. There'll be really the only pressure you have at the top of the tank is atmospheric pressure. So that is my P naught. The pressure that's going to be higher is at P. Maybe I just did this to make sure you're paying attention. So the bottom of the tank, or at any level going down, that's your pressure, and the top is equal to P naught. So what is P naught? So P naught is really just going to be standard atmospheric pressure. Yeah, I was just seeing if you're paying attention. It was my big plan. Okay, that is equal to 14.7 psi. So standard atmospheric pressure, sea level, is 14.7 psi. So what we need to find is how much greater the pressure is at the bottom than at the top. So we're looking for some delta P. So delta P is going to equal the difference. The larger value will be at the bottom, the volume of the pressure at the bottom minus the pressure at the top. And then that's just going to equal rho GH. All I did here is I just rearranged that equation 6.4 to get P minus P naught. All right, so what is rho? So for gasoline, from table 6.1, the density of gas is equal to, let's see, 1.32 slug per cubic feet. Okay, so going back to my equation, so delta P is equal to rho, so that's my 1.32 slug per cubic foot times gravity, my 32.2, oops, 32.2 feet per second squared, times the height. Well, the height is 18 feet. Okay. Let's look at our units. I'm going to get an answer here, but I don't think we're going to like the units. On the numerator, I have foot squared. On the denominator, I have foot cubed. So my unit, let me get the number. The number is going to be 765.1. Let me actually verify that. So 1.32 times 32.2 times 18. Yep, 765.1. And the units will be slug in the numerator per foot second squared. Well, that's not what I want. So what do? I want pressure in pound per square inch, right? So I have a bit of a problem that I've got it in terms of slugs and not pounds. So let's go ahead and think about the relationship here between pounds and slug. So I'm going to do this off to the side in green. So I know that weight is equal to mass times gravity. And I know then that pound is equal to slug times foot per second squared. This is what we did last time. Okay, so what I really want to do here is I want to get rid of slug and put it in terms of this pound foot per second squared. So on the right side, I'm going to isolate slug. So slug is equal to pound second squared divided by foot. Everybody get that? So over here, this is equal to 765.1. Instead of slug, I'm going to put pound second squared per foot. And then I still had in the denominator the foot and the second squared. So what this is instead of slug, I've got this from that. Actually, I'm not taking it in that way. I'm taking it in that way. Okay, so that's equal to 765.1 pound. Oh, second squared has crossed out. Pound per square foot. And what I'm left with is a pound and square feet in the bottom. Cool. Is that the unit I want? What I want is a PSI, not a PSF. Pound per square foot, that would be a PSF, pound per square foot, and it's not really used ever, hardly ever. Okay, so what I want is a PSI. So I can go ahead and convert that, and I'll say delta P is equal to 765.1 pound per square foot times, I know there is 1 foot is 12 inches. That has to both be squared. And so the change in pressure is 5.31 pound per square inch, PSI. So there's more pressure down below than there is on the top. Absolutely. So that's actually a big takeaway, that my pressure color should I use? Maybe I guess I'll use black. That the pressure, so the big takeaway here is that pressure increases with depth. We all know that, right? We all know that. But notice how it does not depend on the diameter of the tank. Were we given the diameter of the tank? We actually weren't. We weren't even told how big the diameter of this tank is. I mean, it might be like at a huge storage facility, and this is 30 feet across. It could be a glass of water, and it is 3 inches across. It doesn't matter. The pressure is only related as dimensionally to the height. So if I had a 18-foot glass of water, yeah, this is how much the pressure is going to be at the bottom. And then let's talk one more thing. When you talk about the the delta P, there's a name for this. This is called the gauge pressure, the delta P. That is the gauge pressure. If I wanted to get like the actual or absolute pressure, I would go ahead and add the atmospheric pressure. So to get absolute pressure, which is the actual pressure 18 feet down, I would add, my colors get me into trouble. I would add atmospheric pressure. So the pressure, I could do that over here. The pressure is equal to the 14.7 plus delta P. So 5.3. So the pressure at that depth is about 20 PSI. It's not asking for it, but if it were to ask for absolute pressure, that's what you're talking about. When you're talking about pressure, you really do need to be clear what kind of pressure are we talking about. And if you say the pressure is 5.7 or 5.3, and in fact it's actually 20, well, if anybody told you that the pressure was 5.3 PSI, you kind of know that they must be talking about a gauge pressure because that's less than atmospheric pressure. Okay. So keep that in mind. Okay. So this was a good problem. I like some of these big takeaways. When I'm selecting the problems I want to go over, because this one is not a homework problem, I try to get ones that I think just have kind of the biggest takeaways. All right. Now the next one is a homework problem. Blood pressure is conventionally measured in dimensions of millimeters in a column of mercury, and the readings are expressed as two numbers. For example, so I did a recent reading that I had personally. It was 136/87, a little bit high, not terribly high, just a little bit hypertense. The first number is called the systolic value, and it is the maximum pressure developed as the heart contracts. The second number is called the diastolic reading, and it's the pressure when the heart's at rest. So it goes higher and then lower, higher and then lower. So there still is a pressure when it's not contracting. That's your diastolic. And then it goes up to the systolic, diastolic. In units of kPa and kilopascal and also PSI, what is the difference in pressure between the given systolic and diastolic readings? The density of mercury is, that's nice, they gave me the density of mercury, so I don't have to look that up. I'm assuming it's not in the book, and that's why they gave it to us. Okay, so given, we have the blood pressure. The BP is 136/87 millimeters mercury. And the density is 13.54 megagram per cubic meter. That's a stupid unit. Let's go ahead and convert that to kilogram. So that's 13.54 times 10 to the 3 kilogram per cubic meter. Okay, what I need to do is find the pressure difference in kilopascal and PSI. And of course, I'm going to draw a figure. So let's pretend it's like an old blood pressure cuff. I don't know if you've seen this in the doctor's office. There's like a kind of like a column about the size of my Apple Pencil on the machine, and they pump it up, and then you can see the mercury rise, and then they slowly let it go, and it drops down, and they read the systolic, and then it drops down more, and they read the diastolic. Okay, but let's draw that. So I have like a column of mercury. Very small here. Okay, so the highest it's going to get is up here at 136 millimeters, or I don't need to say mercury, there's mercury in it. So it's going from 136 down to, not to scale, 87 millimeters. Okay, so I care about this height, right? Height difference. So the height that it goes from between the bottom and the top is the 136 minus 87. So the height is, that is 49. Okay, so the height is 49. All right. Now let's get started. What do we want to do? So first of all, recognizing that the delta P is from the height difference. Sorry, my mom. Height difference of 49 millimeters. Okay, so my equation, I'm going to use that equation 6.4 again. So the pressure is equal to the pressure not plus rho GH. This is equation 6.4. Hey, Winnie. Winnie's been with me here. Do you want to go get in your bed? Yeah, sorry, just a second. You want to go get in your bed? Okay. Okay, so this is exactly what I'm going to use. So delta P, we're going to do the same thing that we did last time in the last problem. Delta P is going to be the pressure minus P naught, and that is equal to rho G, rho G H. So delta P is equal to rho. That was my 13.54. So my density of the mercury is the 13.54. So 13.54 times 10 to the 3 kilogram per cubic meter times gravity, which would be 9.81 meter per second squared, times the height. I'm talking about 49 millimeters. I'll go ahead and put that in as 0.049 meters. Okay. So what is going on with my units? In the top, I've got meters squared. In the bottom, I have meter cubed. So I'm going to get an answer in terms of kilogram per meter second squared. So delta P. So let me do this. So we've got 13.54 times 10 to the 3 times 9.81 times 0.049. Okay, 6508.5. 6508.5 kilogram per meter second squared. All right, so in the last problem, we had this, and we got the funky unit in terms of slugs when we really wanted it in terms of pound per square inch, so pound. It's the same thing that we have here. We want the unit in terms of Pascal, which is a Newton per meter squared. And we don't have that. We have in terms of a kilogram. So what we need is a Pascal. So what we need, Pascal. We know that Pascal is a Newton per meter squared. Okay, that's what we're looking for. We're looking for a Newton per meter squared. And so if I start off with weight equal to mass times gravity, in terms of units, that would be Newton is equal to kilogram times meter per second squared. If I solve this for kilogram, a kilogram then is a Newton second squared per meter. Let's put that in my answer here. So I'm going to say this is equal to 6508.5. Instead of kilogram, I'm going to do Newton second squared per meter. So instead of kilogram, I'm doing this because I'm putting that in. And then I'll still have in the denominator meter second squared. Okay, so look at this, and you can see that the second squares will cross out, which is good. And I get Newton per meter squared, which is great. So I can say my delta P is equal to 6508.5 Newton per meter squared, which I know is a Pascal. So that's 6508.5 Pascal. And let's put it in terms of KPA. I think it actually asks for it. Yeah, in terms of KPA. So that there's 1,000 Pascal in a KPA, kilopascal. So that's 6.509 kilopascal. That's my answer, and I'm sticking to it. But it said it also wants it in terms of PSI, so practice with this. So convert to PSI. You really can't get enough practice with this. So delta P is equal to 6508.5 Pascal times, it is, let's see, 1.450 times 10 to the minus 4 PSI per Pascal. So my delta P is 0.944 PSI. So we're looking here for the gauge pressure. It's the pressure between the diastolic and systolic readings. The gauge pressure is 6.51 kilopascal, or slightly less than 1 psi. Kind of gives you an idea of kind of how substantial a psi is compared to a pascal, because this is like less than 1 psi is 6,500 pascals. So just kind of, it's good to get a feel for that. Okay, and then we are coming up to our last problem. Doing really good on the time. It's because no questions. I'm not pausing to see if you have any questions and trying to think about what questions you might have. I love this problem. This is the Archimedes problem. An ancient king's supposedly golden crown has a mass of 3 kilograms, but was actually made by a dishonest metalsmith from an equal mix of gold and silver. So, if Archimedes suspended the crown from a string and lowered it into water until it was fully submerged, if the string was then connected to a balance scale, what tension would Archimedes have measured in the string? If the test was repeated, but this time with the crown replaced by an actual 3 kilogram block of pure gold, what tension would be measured? Okay, so I have a video. So let me stop sharing for a moment and let me grab my video, and then I'll share that. It's a good video. If you don't mind some partial nudity. Oh my God, the Archimedes, it is no longer available. Oh, this sucks. I really like this. Let me search Archimedes King Crown for engineering students. I want to get something that's not too long. Okay. I have a few that I can do.
Let's dive into the gene.
Let's see. I don't think I want a short. I think I want a real video.
Here's a great story about a gold.
Oh, this one's 9 minutes. That's too long. Um, let's go with the cartoon. Okay, so now let me share my screen. Window will be, I'm going to share, oh, let me include sound, and it will be Chrome. So I'm sharing my Chrome, and let's hope this is a good video. Let me turn on closed captioning. It is just like 3.5 minutes. So let's hope this is good. I think I have it running on full speed. It should be. It was just that other guy that talks so slow that I didn't want it on. I wanted faster than that. Okay, here we go.
Have you ever had a brilliant idea in the most unexpected place? More than 2,000 years ago, a man named Archimedes, one of the greatest minds of ancient Greece, was said to have done exactly that. Archimedes lived in the city of Syracuse. He was admired not only for solving puzzles, but also for his deep studies of shapes, numbers, and motion. His clever ideas in geometry and mechanics made him a trusted advisor. So when the king of Syracuse had a puzzle too tricky for anyone else, he turned to Archimedes. The king had commissioned a crown of pure gold, but when he received it, something seemed odd. Gold is unusually heavy for its size, and the king, who often handled coins and bars of gold, felt that the crown looked a little too bulky for how heavy it was. Was the goldsmith honest, or had he secretly mixed in cheaper silver? The challenge: test the crown's material without damaging it. According to a later story written by the Roman author Vitruvius, the idea struck Archimedes while stepping into a bath. He saw the water level rise as his body sank down. That meant the amount of water pushed aside matched the space, or volume, his body took up. And here was the key. If you know how much something weighs and how much space it takes up, you can judge how packed its matter is. Gold is much more tightly packed than silver, so a crown of pure gold and one mixed with silver might weigh the same, but the silver one would occupy more space. The legend says Archimedes leapt out of the bath and ran through the streets shouting, "Eureka! Eureka!" Greek for "I found it." Whether or not he truly ran naked, the discovery itself was worth celebrating. Archimedes compared the king's crown with a lump of pure gold of equal weight. If both displaced the same volume of water, the crown was pure. If the crown displaced more, its material was less dense. Proof that cheaper silver had been mixed in. Today we can put numbers to it. Gold's density approximately 19.3 grams per cubic centimeter. Silver's density approximately 10.5 grams per cubic centimeter. But here's the subtlety. The difference in water displaced is small and nearly impossible to judge just by looking. Historians think Archimedes may have used a hydrostatic balance, a careful weighing in air and in water, to make the test practical. From ideas like this, Archimedes went further. In his treatise on floating bodies, he set down a general law. Anything dipped in water feels lighter because the water pushes it up with a force equal to the weight of the water it pushes aside. This principle explains why ships float, why balloons rise, and why submarines dive. The crown story may be legend, but the principle itself is real science. So next time you take a bath, watch the water carefully. Behind that simple ripple lies one of the most elegant ideas in science: the link between weight, volume, and the upward push of water, first noticed and then proven by Archimedes.
Okay, so that was pretty good. I think I'll put that in rotation now. Okay, so the previous one had live action actors, and there was this old man who kind of gets naked. I mean, you don't see anything; it's all covered up. But yeah, it was kind of funny. It's like kind of the last thing you want to see is him jumping out of the bathtub and yelling "Eureka!" Um, Maybe it is better in cartoon form. Okay, so now let me go back to sharing my iPad. Let's see. There we are. Okay, so we're going to do this problem. Okay, so we have these densities of gold and silver. Here, let's go ahead and write down what we have. So we're given that the crown, so it's something that's not easy to get like the volume of because it's it's an such an irregular shape. The crown has a mass of 3 kilograms. And we know that the density of gold is a 1.93 times 10 to the 4. That is kilogram per cubic meter. And then the density of the silver, slightly less dense at 1.06 times 10 to the 4 kilogram per meter cube. And what, I'm not going to write down what we need to find and everything. Okay, let's do a of like a free body diagram, I guess it is. Yeah, let's actually do a free body diagram of the crown in the water held up by a string. So here's my crown. So some sort of crown shape. Not an artist. Okay, so you have a tension force on the crown. And of course, you have the weight of the crown going down. I would put that at the center. And then you have a buoyancy force of the water kind of holding it up. And so if we do a force analysis, equilibrium, if I do sum of forces in the y direction is equal to 0, positive up, I would have tension plus the buoyancy force minus W equals 0. So I could say the tension force should equal the water, the force of the weight plus, minus the buoyancy force. Okay. So what is the buoyancy force? In the textbook, and this was in the slide, we saw that the buoyancy force is equal to the density of the fluid times, oops, that should not have a G there, the fluid times gravity times the volume of the object. This is equation 6.5. And also, let's just put in here that we know that the weight is equal to the density times the gravity times volume. And this is equation 6.3. How are we going to use these? So, starting off with this equation 6.3, weight is equal to mass times gravity. That's equal to the density, let's say the density of the crown times gravity times the volume of the crown. Well, gravity's on both sides, so I can cross that out. So I can rearrange and I can actually solve for the volume. So the volume is equal to the mass divided by the density of the crown. So it's equal to 3 kilogram divided by oh, yeah, so what am I going to use for the density of the crown? Because this is the looking for the density of the crown. So for the density of the crown, let's just go ahead and take an average of these two. Is equal to the average. So the average of those two is equal to 14.95 times 10 to the 3 kilogram per cubic meter. I just decided to work in times 10 to the 3 instead of times 10 to the 4. Okay, so 14.95 times 10 to the 3 kilogram per meter cubed. You can see where this is definitely going to give us a volume in terms of meter cubed. So the volume is equal to 2.01 times 10 to the minus 4 cubic meter. Okay. So now I've got the volume of the crown. So let's get the buoyancy force. The buoyancy force is going to be the rho GV. The buoyancy force, and I need the buoyancy force because I need that from my equilibrium equation up there. Okay, that is equal to the density of the fluid times gravity times the volume of the object. Well, the density of the fluid in this case, the fluid essentially in the bathtub, is equal to that's water. So that's equal to 1,000 kilogram per meter cube. Times gravity is 9.81 meter per second squared times that volume that I just got. The 2.01 times 10 to the 3, excuse me, times 10 to the minus 4 cubic meters. Okay, so this looks good. Kilogram meter per second squared, that's going to be giving it to me in newtons. So the buoyancy force is equal to 1.969 newtons, which is exactly the unit it should be. All right. So now what? Now let's go to this equation from the equilibrium. That'll give me the tension. going down there. So the tension from my equilibrium analysis is equal to the weight minus the buoyancy force. So that's equal to weight would be mass times gravity minus the buoyancy force. So that is equal to the mass was 3 kilograms. Gravity 9.81, that was given in the problem, meters per second squared, minus kilogram meter per second squared, so that's going to be a Newton, minus the buoyancy force, which was 1.969 newtons. Okay, so the tension, let's call this the tension. This is the tension in the string from the mix. And I said the mix was like, I think we took an average of the densities, half silver, half gold. So the tension that you'd get on the string from the mix of an impure crown, 50-50 silver gold, that turns out to be 27.46 newtons. Which is interesting, but you really can't prove that it's not, that doesn't prove anything. But if we repeat this, and instead of doing that mix density, which is this, what I called the density of the crown, and I had it be just the average of gold and silver, this is what I used over here to get the volume. And then the volume gave me the buoyancy force. And then I found the tension. That's the tension of the mix. If I repeated all of that with pure gold, so pure gold. So repeat with the density of the gold instead of the average density. I won't take us through these steps. Just trust me. What you get is that the tension, if it was all gold, is equal to 27.91 newtons. So, trying to figure this out. If it was all gold, it would have more tension on the string than if it's the mix. Kind of the problem, though, is that it's a very small difference. Do you guys see the difference between these tensions? Yes, there is a difference. If you look at that, I did this earlier and I calculated, this is only a 1.6% difference in tension. If a less dense material is used. This is going to be really hard to figure out. And this is if like the bad metal, the dishonest metalsmith, if he used gold and silver 50-50. If you used zinc instead of the silver, you used zinc or iron, other filler materials, it's a bigger difference. So the moral of the story here is, yeah, you can absolutely prove that this is not pure gold. But it's a small difference. And it would be difficult to measure. I guess I keep thinking about Archimedes and whether he was able to measure all this. I guess maybe he was able to measure all this. We need to, give him his props for doing this. But if it was a much lesser material, then there's a bigger difference. It would be more noticeable. Okay, so that is all I've got. See, that's all I've got. Okay, so that's all I've got. And check your email for information on your homework. This was the first lecture into fluids. Next week, we'll be doing the second lecture into fluids, and then we're going to go on into heat, heat transfer, thermal and heat. Okay, so let me know if you have any questions, and out of here. Bye.